Good morning, everyone. Thanks for joining in. We are at the Waterloo Institute for Nanotechnology, WIN, which is at the University of Waterloo, acknowledges that much of our work takes place on the traditional territory of Anishinaabe, Haudenosaunee, and the neutral people. Our main campus is situated in the Haldeman Tract, the land granted to Six Nations, that includes the 6 miles on either side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, scholarship, teaching, and community building, and is coordinated with the Office of Indigenous Relations. We are so happy to have Professor Ali Beskok, who is here and will spend the entire day giving the WIN Distinguished Lecture. He has a very distinguished career, and he started after finishing his PhD from Princeton. He moved to Texas A&M, where he started his academic career. Then he moved to Old Dominion University, and later on, he moved to the Southern Methodist University, SMU, from where he is coming as a chair of mechanical engineering, and now currently as the George R. Brown Chair in Mechanical Engineering, as well as the Associate Dean of Research, Innovation, and Industrial Partnership at the School of Engineering. To give you a bit of anecdote, my inspiration of the work on my micro nanoscale started with his talk. When I met him, he gave I think it's in ICTP, International Center for Theoretical Physics at Trieste. We spent a week with Ali at I think maybe 2 weeks or something. 1 week, he was giving a lecture on these microscale phenomena. Well, I will not say which year. And that gave me an inspiration. I was a young academic at that time, assistant professor, but that gave me an inspiration to work in this kind of microscale phenomena. So I'm so happy that Ali took this opportunity and having this having this opportunity to have him here and spending time with us and providing some inspiration talk about some of the current work happening. So, Ali, thank you, and please, the stage is yours.
Thank you. Well, good morning, everyone, and it's my honor to be here. And I'd like to thank Sushanta for his kind invitation. And I'm honored to see so many of you interested in this. And now I really hope I can deliver so that I don't feel guilty. So the title of the talk is Electrical Characterization and Manipulation of Biological Cells in Microfluidic Systems. But because I also wear a hat of being an administrator, I would like to tell you very briefly about Southern Methodist University, which happens to be a private institution that's about 5 miles north of downtown Dallas. And Dallas is the 3rd largest city in Texas, but with Fort Worth together, it is the 4th largest metroplex in the United States with about 7.8 million people. And it's a pretty big surface area as well. It's being the only private university within Texas itself, Dallas. We have approximately 12,000 students, and 5,000 of them are graduate and 7,000 of them are undergrad students. And, it is actually a university that's been around for about 115 years. So in Law School of Engineering, we have 5 particular departments: civil and environmental, computer science, electrical, computer, mechanical, operational research, engineering management, like industrial engineering, and also we have multidisciplinary programs. And here are our engineering buildings. Our labs are actually across the highway, which is a walking distance, but not pictured here. Just about our school has about 900 graduate students and 810 undergraduate students with more than 7,000 alumni. And basically, we have 86 faculty members. This is Professor J.C. Chow, who happens to be my collaborator. And average graduate student faculty ratio is 9:1. So that's it about assembly. But let's talk about microfluidics. So it's an emerging technology that allows development of new approaches to 3 things: synthesize, purify, rapidly screen. And you do that for biological, chemicals, and materials. And you can do it in a massively integrated miniaturized platforms. So this is basically the promise of the microfluidic technology. And indeed, your probably familiar that the idea is actually to shrink large chemical, chemistry laboratories onto a chip size with the handheld devices. It is the laboratory chip technology which utilizes, or does detection of biological chemicals and so on in a handheld device. It is really an interdisciplinary part of work, and when you look into typical LOC components, you see samples preparation, flow control, and detection. And today's talk is going to be this red underlined topics of separation, concentration, and sensing. However, our lab has also done pumping and mixing as well. So the objective of this talk is to introduce you to dielectrophoresis, and its counterpart is, or not counterpart, and its part is an impedance spectroscopy for detection. And I'm going to show biomedical applications of this. I decided to put something actually slightly different here, because just as a pandemic was coming in, we were looking into antibody-antigen interactions and detecting this on, chips. And we built basically this device here, which has, only like 3 electrodes, but the electrodes have nanorods on them. As we functionalize these nanorods with antibodies, we can actually make an antigen detection using spectroscopy techniques, and we were able to actually show 1 nanogram per ml of IgG, from a high conductivity buffer solution within a minute. And this is something that we published in April of 2020, as the pandemic in the US has began in March. Following to this work, we have also looked into extension of this to detect neutralizing antibody for COVID infection. And we built a chip that does this impedance-based measurements. And interestingly enough, this curve seems to be very similar to a very large-scale analytical device that was approved by FDA to detect the amount of neutralizing antibodies from blood plasma. And our technology cost about 75 cents per test. So, of course, the large-scale device was much more expensive to run. But so I'm not going to be talking about the details of this, but instead I'm going to talk about some earlier work that we have done. And we were interested in sample separation and concentration. And the key is that if you're dealing with, okay, this supposedly works. Okay, so if you're dealing with a clinical sample, you may have a lot of organisms per unit sample. However, the situation changes if you would like to look into, like what's in a little droplet of water, milk, and beverages, and so on. And one of them would require basically sample separation. And here is the example. For example, circulating tumor cells from blood, these are the bad guys, can perhaps be separated from other blood cells. But then if you're dealing with, sample concentration need, assume that you just go and take a little droplet from a pond and you'd like to see what's in it. Well, which is fine, because if you use a PCR-based detection, even a 10 microliter sample, we can actually, amplify the DNA and say something was in there or not. But the problem is that one organism per 10 microliter requires, 100,000 organisms in a liter, which means that you need to go to a high throughput system and do sample concentration and get everything you can concentrate, so then you can actually do a separation step to see what was in it later on. So basically, I would like to pose a question and try to answer that throughout the talk. Can AC electrokinetics be used for sample separation and concentration? So what we're going to have here is that AC electric fields, and it will induce various effects like AC electroosmosis, dielectrophoresis, and electrophoresis of the particles, which is also known as electroacoustics. But there are other forces and effects in there. For example, you have electrothermal effects, because these are, there's Joule heating in the system as you're putting electricity through. There's gravity, things will settle down. There's ground motion of tiny particles. There are going to be van der Waals interactions and electrical double layer interactions between particles and surfaces and so on. And these are the things that's harder to control, but perhaps we'll be able to control the AC electrokinetic effects, and hence we will know or we will build something useful. So most of the things that we do in our work utilize basically glass slides that has deposited electrodes on it. These electrodes can be interdigitated, like shown here, which means that at any time of or any instant of polarization, one end will be positive, the other one will be negative. And as you do that, you can actually put some geometric features on it too, and assume that this column is positive, that's negative, and there's some geometric features, which I'll tell you why that's important later on. So we do a system like that, and we may, build a microfluidic system, or actually we just put an O-ring and put little particles in it and put the cover glass, and we basically image what happens from the bottom. As you look from the bottom, there's going to be gold electrodes and the glass, in between them. In the movie, I'm about to show you the light parts are going to be the glass, and the darker parts are gold. It's not totally opaque because it's a very small, deposition. So when you look in between the electrodes, so one is positive, the other one is negative, and it's totally, going through any electric fields. And let's look into the motion of 800 nanometer gold nanoparticles in this solution, and with 30 micron electrode separation. And this movie is actually repeating 6 times, and then we start, but we start everything Brownian right now, and then 100 hertz, and chaining happens around 1 megahertz. Here we go. And interesting vibration happens in 10 hertz. So we did these experiments systematically. At different voltages and frequencies, and we also some consistent cases. For example, frequency-based consistency. Of course, the value of the voltage is too low here, but you saw the vibration of the particles, and then you saw a case where the particles were leaving the gap and going to the size of the electrodes and particle chaining. So indeed, the first thing that we have seen is known as electrophoresis or electroacoustics of the particles. Those are the particles vibrating. Then you see a case where the particles are leaving these electrode gaps. That's actually a convective flow. That is actually called AC electroosmotic flow. And it is quite effective if you happen to have a thick electrical double layer. If you go into a high concentration buffers, it's going to get thin, and this effect basically is diminished. However, if you're using high conductivity buffers and you use large electric fields, there's Joule heating based effects, which actually induces electrothermal motion, which I'm not going to talk about in this talk. But I'm more interested about this chamber illusion, and that is actually in response to dielectrophoresis, and it creates highly reputable structures. And the forces that it induces are basically reversible. So if I let go of the electric field, I can release those particles. So which is good. And then it's a non-invasive and reagent-free tool for sample separation and concentration. Let's see how well it works for synthetic particles as well as biological cells, and let's see what are the limitations of it. So dielectrophoresis is the motion of polarizable particles that are suspended in an ionic solution and subjected to a specially non-uniform electric field. So if the particles are more polarizable, they will go to the large electric field grading zones, and that's positive dielectrophoresis, which means that they will be stuck there. But negative dielectrophoresis are particles that are not as polarizable as media, and they will be repelled from these zones. So if you push things away, you don't have a control of it. If you capture them, you actually grab them, right? So basically, we see these two different effects. So the movie shows real-time images of 1 micron and 4 micron particles, I think it's polystyrene, at first 20 megahertz for 10 seconds, then 400 kilohertz. I told you that earlier on, it is possible to put features on electrodes. So in this case, for example, polarization of one electrode flow versus the other is changing constantly at 20 megahertz. So the importance of this geometry is that at a given polarization, if this is say positive, and which means that this square region becomes a potential field minimum. So which means also that a negative DEP will be effective there. So first we're seeing that both particles are going to the field minima, so these are showing negative DEP, and then we switch it to 400 kilohertz. Large particles are still staying in the middle, and the small ones are chaining, and that's the positive dielectrophoretic response. So why does this happen? Well, it happens because these are polarizable particles, and there is a dipole moment that will create a force and a torque. So in the simplistic form, if you say point dipole method, there are other methodologies, of course, Maxwell stress tensor method can be used as well, but that's more thorough. I like simple things, but even this is kind of complex for me. So basically, you can have a dipole moments for spherical particles given with this formula, where A is the particle radius, and E is the electric field, and K is the Clausius-Mossati factor. This is actually the key that's going to determine whether you will have a positive or negative dielectrophoresis. So if you have a general electric field with a phase angle, and you can actually create, very interesting effects that's going to end up with time average DEP force, which is of course the real part. But there are two things that you can see. One of them is force due to non-uniform electric field strength, because gradient of E square is coming here. And there's also force due to non-uniform phase angle of electric field. So I would like to first demonstrate the complex one. Too many imaginary and real numbers there. And so what we have done, like others have done too, is that we create a 4-electrode system. And then if a polarizable particle is in there, and then if you put an electric field with a phase angle, you can induce a torque on those particles. So the movie here shows response of cervical cancer cells to a rotating electric field. And there's a couple over there that rotates faster, some are slower, some are extremely fast. People in the field look into these kind of rotational speeds to make sense out of the dielectric properties of these kind of cells, which is fine, but it's actually too complex for a mechanical engineer to get into that much electrical engineering stuff. So basically, we were more interested in DEP forces with constant phase electric fields. And for that, the DEP force is given in that formula. And there are 7 parameters here. P subscript shows for the particle, so you have the permittivity and conductivity of the particle, permittivity and conductivity of the fluid, particle size, applied electric field frequency, and the electrode design will actually determine the electric field. So if you have a spherical homogeneous particle, you will see that you can create a complex permittivity, which will use the permittivity, and then the ratio of conductivity divided by the applied frequency that can actually induce a complex permittivity. And when we take the real part of it, we will be finding different frequency-based response. So that's the key thing here, that why things work with positive versus negative DEP. So let's go further here, and don't worry about that equation up there. But if you have a solid homogeneous particle, are you going to have a positive or negative, Clausius-Mossati factor? Theoretically, it starts from 1 and goes to negative half as a function of frequency, but the outcome is going to be determined on the conductivity of the fluid that you're using, because which one is more polarizable is the question here. Is this the particle that will give you positive DEP, or is this the fluid that's going to give you negative DEP? So we did this, theoretically, looking into different conductivities of the buffer, and you have a very interesting, say, pure or ultra pure DI water, which will be hard to have in a lab, but you will have a 1, and then it transitions within this frequency range and becomes negative half. However, after some sort of the threshold, you may not even see any positive DEP, and then high frequencies may give you negative DEP, or you can, in a very highly polarizable fluid, you will only see negative DEP for these particles. So as I tried to allude to it, if the real part of the Clausius-Mossati is positive, you have positive DEP, otherwise you have negative DEP. So let's see if this is correct or not. So we started to build order of magnitude analysis-based phase diagrams so that we can understand, what to expect. So the key is there are 7 parameters here, and I can only, plot 2-dimensional. So we fix the interdigited electrodes with the voltage being 10 volts. Electrode separation is 15 microns. And here's the conductivity versus frequency diagram. And we have done systematic studies for 1 micron polystyrene particles to show that at different frequencies you'll see different things. Well, this picture tells me that at high frequencies, not that way, sorry, this at high frequencies, mostly we expect negative dielectrophoresis theoretically. And there's a zone of positive dielectrophoresis in a certain frequency range. And that's very much a function of the conductivity. So at high conductivities that we have no chance of positive DEP. And also there are other effects like Brownian motion of particles always there, but then axial electroosmosis may be dominant. And at one point, as the double layer thickness gets smaller and smaller, that's not important altogether. We were trying to use this for sample concentration from apple juice and 2% milk. And those are basically the conductivities of those fluids versus blood plasma versus PBS solution. So obviously there are big differences. And you can actually see that in the eye water over here in low conductivities, I can see the very nice particle shading, but we lose the effect of DEP. We expected negative DEP, so I was hoping to see that these particles will be coming on top of the electrodes. These are electrode gaps here, but we didn't observe that. So obviously, DEP is losing its effectiveness, and that's a big concern because all physiological media is mostly like 1.5 centimeter conductivity, and then this method may not be useful at all. So our observations are that DEP becomes ineffective in high conductivity and physiological buffers. However, it's effective in low conductivity buffers. Then we have shown, and I'll show you in a few slides, that when you put mammalian cells in low conductivity buffers, they show transient variations of their properties, and that's not desired. So the ultimate goal is dielectrophoretic separation of two cell lines, and basically, unfortunately, this is selected by trial and error, and that's not really effective, right? So there must be a better way of doing that. So that's why we got interested in trying to measure dielectric properties of these cells by using microfluidic impedance spectroscopy. So, about 2012 era, we built this simple device, which is a microchannel, and we have basically 2 electrodes on top and bottom, and we fill this with a fluid with cell suspension. And the key is, of course, you need to create an electric circuit model of this kind of a system. And when you do that, you have first the electrode polarization effects, especially becomes very dominant with small electrode size and high conductivities. And that's handled by constant phase element model. And I'm going to talk about that very briefly later on. And then we use the Coco model and Waxwell-Wagner mixture model, which basically separates the properties of the fluid and the cells itself. And that basically gives us the Clausius-Mossati factor. And then you may go further in saying that this is a single cell. I would like to see a cell as a cell with a cell membrane and a cytoplasm, or a double shell model, which will also put a nuclear envelope and nuclear plasm in your measurements. So the key thing is that you have a complex frequency-based measurement of the impedance variation, and you have to model all of these things consistently to say something about the properties of the cell. If you know this, then you can draw cell parameters from measured spectra, and if you know the cell parameters, you can simulate what you will be measuring if you did this experimentally. So this is a both way, it can go both ways. And the problem is, of course, it's a nonlinear square fit algorithm that we use to fit all those parameters. And, we can be challenged whether the solution is unique or not. But we have actually, identified methodologies to do that right. So looking into that, we were able to, create this, same design that we have seen earlier. And we entered there with two different cell lines, Jucat, which is human leukemia cells, and B16 is mouse melanoma cells, so they will not be in the same system together, but in a mechanical engineering lab, you can do it. So basically, we put it in different conductivity systems and measured their cross-responsive factor. And as you can see here, okay, I'm sorry. The way that it transitions is a function of frequency from negative to positive. If you find a way that one is positive, the other one is negative, then you have a chance that you can separate them. So we basically stained, the B16 mouse melanoma cells, and we were able to mostly, capture them with positive EP here. And Jucat cells mostly show negative DEP, but there are exceptions, as you can see. But if B16 is captured here, as it should, due to the positive DEP, I should be able to wash this over. So the things that are, the Jucat cells mostly will wash away, with the exception of a few that's also showing positive DEP, which is fine. And we did these experiments, and we were trying to find, can we do it? That conductivity. And theoretically, we can go as low as this, but that conductivity is really giving you a very minor cross-responsive factor. And if you just increase the electric field, you have other effects that you're dealing with, and it didn't work. Well, that's fine, 0.06 Siemens per meter, but the problem is that you need to go 25-fold dilution for this to work, and it's not a good idea. So we have shown something that's semi-useful. Then we were more interested in about trying to look into the electric properties of biological cells in a flow-through system. We basically created SU8-based microvalves, and we have an electrode in the bottom, electrode on the top. So as the fluid basically flows and there are cells in it, first we tune in to a certain frequency so that the cells will see positive DEP. So what will happen is that those cells are going to get into these egg crates that I have created, because that's where the electric field gradients are high, right? And then once they are actually captured, I can measure the electric properties of that cells that are captured in the system, and then switch the frequency and eject them using negative DEP, because negative DEP will push them out. So this movie actually shows that it works. The valves are gradually loaded as the fluid is basically ballistically coming from right to left. And then we turn on our impedance measurement. Here's the magnitude versus the phase angle. And you have to study that. And then switching the electric field, you will see that these are being empty. It is not a very clean movie because of things passing by, but it works to a degree. So it made to the cover of Analytical Chemistry 2018. So how do you analyze something like that? So fortunately, we can take a picture and we can see with a total of 576 valves, 86% of them were filled. So which is good. So with one shot, we are measuring approximately 400, 500, valves and cells. Well, here's the problem. The geometry is that there's an electrode and top electrode, and these modules are periodically repeating themselves so that they are like a parallel circuit. So that we take each of them as a single element, and then we put them together as a parallel circuit. And we couldn't use the single shell and double shell models and so on. Instead, we said, let's do it the simplest possible way. There's electrode polarization, and there is the resistance of the fluid. There's resistance of the fluid in a valve, membrane capacitance, and cytoplasm resistance. And for an open system or unfilled system, you don't have the cell parameters. So knowing that how many of them are filled versus how many of them are empty, you can actually create a parallel circuit model and be able to make a measurement of approximately 500 cells. So we did this at conductivity of 0.05 Siemens per meter. The top red figure is going to show you cytoplasm resistance, and the left, which is blue, is the membrane capacitance. As you can see, there are some changes in the membrane capacitance. Not as significant perhaps, but there is more change with the cytoplasm resistance. It's because the ion channels on these cells, and these are PC3 prostate cancer cell line, are basically constantly interacting with that media, and then it shows this variation. It's that variation that actually, bothers me, because I cannot pinpoint a single parameter for these cells because the cells are not in a happy medium. I always tell my students, like, put somebody on top of Mount Everest and then observe their, fight for their life, and then make a judgment about humankind. And that's what we're doing here for these biological cells. But despite that, we were able to, alter, for example, pH. And I would expect time periodic variations in these properties. The reason I'm not seeing that is because of these temporal shifts that are happening. So in order to use these kind of techniques, you have to go to high conductivity and hope that it works. Otherwise, everything is going to be in a transient scale. So let's look into practical limitations. So the lab-on-chip devices must work in physiological buffers to avoid sample dilution and time-dependent variations in the electric properties of cells. And we also see that DP and DS becomes ineffective for high conductivity solutions. And we think that the reason for this is electron polarization effects. So it always comes back to engineering somehow. So technically, if I'm making an experiment, that's our experimental data, and the fit is total of our, fit of our model, and then we would like to extract what's happening to the cell suspension in this kind of conditions. I forgot to tell. 1.5 siemens per meter, high conductivity buffer. This is not what I expect. Theoretically, I would expect polarization of the electrodes and then polarization of the cell membrane, which is what we call beta dispersion. This is what I was trying to measure, and which means that the cell data has to come, flat, and then do this, and I cannot see that in my measurements. So, how to reduce electrode polarization? That took us about maybe 3-4 years to think about it and try different things. And we actually did a nanoparticle deposition on electrodes to deal with that. And just for sake of time, I'm not going to tell you the methodology. If you're interested, please read the paper. But the key is that if you do basically, particle deposition without proper using of the masks, you can have actually, nanoparticle overlap between different electrodes. An electrode system like this will be useless for us, of course, because any polarity, they're going to be connected to each other. But we were able to build these dielectric structures that looks like kind of like a carpet surface. And which one is? So this is gold, this is glass, and this is bare, and this is the deposit. You'll see that interface is not pretty reasonable. And these are ACM pictures up there of the dielectric structures. Let's see what it does for us. So we did the same thing for that device that I showed the movie of with the micro valves. This time the valves are square. And as I alluded in the previous slide, the planar electrodes did not work very well, but the dendritic electrodes did. So I can actually understand what's happening here, and that's related with data dispersion. So the methodology worked extremely well. So the question here is, can we come up with something that will enable us to determine what to expect before we even build a device? All right. So we basically created, again, a capacitor plate design up there, which was basically a large electrode, 4 micron diameter with various heights. And we were also changing the conductivity of the fluid. The effects I'm showing you here are quite minimal because I'm using very large electrodes. All right. So as the electrode shrinks and the conductivity increases, these variations in impedance gets very wild and it spreads through the entire frequency regime. So to use this in true microfluidics, we have to really eliminate it. Well, So you make a bunch of experiments, and then you see these figures. These figures look very similar to each other, right? So there must be a way that I can put them all on top of each other, because I'm a fluid dynamicist, and we like non-dimensionalization of things, right? So basically, if you see that the high frequency range is reaching to our solution, you can normalize the impedance with our solution value, and that becomes a normalized value. And then perhaps you can actually come up with a characteristic time scale that's going to normalize your frequency. Characteristic time scale is a function of the electrode size. The height is basically in between the electrodes, as well as the dBi length, because these are ionized fluids, and it's going to create dBi lengths. High conductivities will be maybe down to a nanometer or so. DI water is about 150 micron or so, I'm sorry, nanometer. So it's very much changing, and it will change the characteristic time. So when you do that, all those things sit on top of each other. Here's the phase angle, starts from negative pi over 2, which shows the capacitive behavior and reaches to resistive. And because we don't have inductance in our model, we see these kind of changes, but we are not as interested in such high frequencies. So all of them can actually, be on top of each other. Beautiful. So I could do that for a planar electrode, but then can I do that for, dendritic electrodes? And if I can, what is changing? So we came up with the hypothesis. We say that dendritic electrodes are behaving as if these are, the medium is a, low conductivity medium with a thick double layer. And indeed, here is a Z over R solution versus frequency obtained in 1 cm per meter. Planar electrodes is shown in blue, and GNS is the gold medal structure. At the same conductivity, you can see the difference. One starts from 8 something, and the other one starts from 1 something. Obviously, their behaviors are different. So can we actually model this difference? Why don't we actually shift our time scale for dendritic electrodes with a coefficient C? And of course, tau C is lambda h over d. So that C will be a function of porosity, thickness of nanostructures, and tortuosity. But when you work that out, you can actually put on the left-hand side an effective double layer thickness, because that's the idea, and then the diffusivity within that medium, which is going to be effective as well. So you have the heights here, which are common, and that goes away. So that's the electrode separation. Then you have a way of saying that the diffusivity of ions in a porous media normalized with the diffusivity of ions in a regular media is where it comes. And we found that in a porous media theory, Bergman came up with this correction, and epsilon is the porosity of the medium. So from here on, we have an idea of effective, double layer thickness. So here is basically the red one is the nanostructure. It's the very same red one with a different scale. I'm claiming that it behaves like a planar electrode at this conductivity. Look at the change in the conductivity, 1 versus 0.076 cm per meter. As you see, they basically fit together. So when you put everything together in a normalized fashion, you can see that there is a trend here, all right? So then we went and made many different measurements. And you can actually see that all of them are on top of each other. So I love that because, as you would remember from your fluid mechanics, it's like the drag force versus valence number curve and so on, So it's showing a universal behavior of some sort. So we modeled that with the constant phase element model, which I indicated earlier in my talk, which is this formula here. What it does is that you have, when alpha goes to purely resistive, alpha goes to 0, it becomes purely resistive system. Alpha equal to 1 is purely capacitive. And when you get the overall data and you curve it to it, you actually found a formula like that. So this is now a dimensionless formula. You have to add 1 on it, which means that this behavior should be true regardless of the size of the electrodes and the electrode separation and the conductivity. You can work backwards to actually put dimensional numbers to it. All right. So by working backwards, you can have a good idea to see how much this effect in your electrode is going to come and take over. And if you know that beta dispersion happens around, say, like 300 kilohertz or so, you don't want this to be coming and shielding that kind of a behavior. So, well, so then by using dendritic structures, we were able to, make measurements. And the top figure A and B, one is the impedance magnitude, the other one is the phase angle. The red shows the planar electrodes, and our fits are terrible to that with dashed lines. However, blue and blue lines, blue dots and blue solid lines are obtained in the nanostructured planar nanostructured electrodes. And as you can see, data matches very nicely. Over here, you can also see that when you have cells in it, you're doing pretty well as well. So this basically opened up dielectric spectroscopy in physiological buffers. So in this paper, we systematically came up a way to uniquely actually identify cytoplasm, resistance and cell membrane capacitance as a function of time, which deviations are for scales. This is like 9,999, and that's like 10,000. So the variations are very, very small. And also, membrane capacitance is rather constant. So, which means that these cells are happy in the medium, then I can very easily measure their properties. So, what then we did is that we started to look into drug uptake studies for PC3 cells. Now, of course, my background is pretty thin here, so please don't challenge me on biology. All right, but if you do that, maybe you'll teach me a lesson too. What we did is we used amiodarone, which is a multiple ion channel blocker, and we come with we first capture the cells, and then we measure the dielectric properties. We see that there is no change in membrane capacitance. And by the way, the number here is 10,000. This is 10,005, so it's all constant data, and this is cytoplasm resistance. But more important thing is, of course, the capacitance values. So we go with different dose of amiodarone, and you can actually see an immediate response in the cytoplasm. Membrane capacitance. And let's try this again. So this case here is the lowest dose. This is the lowest dose, which actually peaks and then goes to zero, like to the base value pretty easily. If you increase from 1 microgram per ml to 2 microgram per ml, you're seeing some transients probably will reach to the steady state. And we did this for like 1,000 seconds. But as you go higher and higher, I think the asymptotes of these are going to be changed. And I think we have a more permanent change happening in the system. So we believe that these changes are due to the change in the surface area and the cell membrane thickness, and how these medicines are being internalized on the cell membrane. So as the ion channels are closed, I expected the cytoplasm resistance to remain the same, and we are seeing that. So that makes sense, at least to me as an engineer. So in order to actually do a negative control, we use glucose and aspirin, and apparently the acronym they can actually get in and out of the cell very easily, and their effects are these little bumps, much smaller than others. So basically, the current device can measure the dielectric properties of PC3 cells as a function of time with the input of various drugs, right? So because I used only top and bottom plate, I wanted to use actually like array of electrodes and an array of electrodes so that they'll cross each other, and that's going to be basically creating me little measurement units, just like the battleship. Do you remember the battleship? You say H5 or something. And if there's a cell there, you're measuring that cell directly what it is doing. So you can actually create a system like that and measure the electric properties of cell in a well for that particular well as a function of time, which means that you can actually create quite a bit of statistics about how they interact with the medium and how they react and what happens to their properties. And I think that would be an interesting way to see response of cancer cells to various agents. And you may be then, if you're able to eject the cells using negative DEP, because it should still be effective with the dendritic structures, then I can empty the well that I would like to be, measuring. So it means you can actually harvest those cells. All I need is a couple of $1 million to do the work, but that's the problem. So that is basically what I think, can happen. All right. So, in conclusion, and not bad, DEP is an excellent method for sample separation and concentration in low conductivity media, and microfluidic impedance spectroscopy enables measurement of the electric properties of biological cells, eliminating the guesswork in DEP applications. That's I think is an important contribution there. And high conductivity media is basically leading to large electrode polarization. And I have shown a way to study self-similarity of the electrode polarization effects, which means that by doing this with 1 or 2 well-taught experiments, if everything scales the same way, and it should, you should be able to predict how small can you go, what works, what doesn't work. And then the analytic electrodes enables measurement of the electric properties in physiological buffers, and that we could look into cell drug uptake in these medium. So I would like to acknowledge all my students and some funding agencies. People identified in blue are my former students who have contributed to this work. And at this point, thank you very much. And I'm open for your questions.
A question from the audience.
Can we start this again in case it comes? Yeah. I mean, yeah, I'm sorry.
Oh, good.
Yeah.
Yeah.
Yes.
Right, and then you did it with glucose. The thing is that glucose, we have glucose transporters on our plasma. So glucose doesn't go through glucose by glucose transporters. So because I studied mitochondria, my question is, have you thought of trying to discriminate? Because a tremendous amount of cellular potential comes just because of the transmembrane potential across the mitochondrial membrane. And I just wonder if what you're seeing is an effect on all the other membranes in the cell, because your model is, you've taken it, right, like it's a slimmed down model, and I understand why, but the amount of membrane that's in the cell, depending on the cell type, can be more membrane than there is cytoplasm. So how can you, I think that there's probably many things you can derive from the data, if you can somehow take that into it.
You're absolutely right. Actually, probably touched people about the more long to understand exactly what's happening. And we're doing an integral measurement. And it may be possible to come up with some models that can relate both together. At this point, if you'd like to put more physics into our computing algorithm, you can. But honestly, I don't have the background and the knowledge base to push that through. I need to work with some biologists.
And then a follow-up question is, have you used other cell types? Because of course, cancer cells are transformed. So what happens if you use some kind of somatic cell? Can you try that?
We have not.
That could be potentially fairly.
I see. Thank you for your comment.
Yes. Your AC measurements looks like you're applying things by. That's like several volts. So is you still consider your system linear if you're applying such potentials? Because you're applying impedance, so that's a small, that's a linear.
Yeah.
Do you still see that?
I mean, for impedance measurements, we systematically change the applied voltage, and you can actually see after a certain range where the reactions are coming into play. However, in DP applications, we go with very large voltages. We don't, I mean, we see a general trend of the cells and particles, and you also see a lot of exceptions too. And especially this happens, for particles or cells close to the, corners of our electrodes. So it's not a bulletproof way of doing it, and there might be some nonlinearities over there as you know about that.
Questions? So, well,
Yeah, it's a really fantastic talk. And for the avoid the electrode polarization, would that be possible for example, add a passivation layer on top of that? Would that actually affect your electrical field?
Well, I mean, we tried that as well, and we didn't find it to be as sensitive. Instead, we went to this nanoparticle deposition scheme. But some people have done that, and it affects the electric field and the measurements that you'll be doing. So the bare electrodes are making the measurements. If you put a thin layer of insulator, you'll be dealing with a slightly different system.
Yeah, that's true. Yeah. I hope one other question, but I'll give a chance to other people.
Yes, people, I think I have a couple of questions. In your dendritic electrodes, you have, is it the structure itself can create localized electrical field that can alter the system? And the second part I have is that you have mentioned about the Brugmann correlation, but if you look at the Brugmann correlation origin is on spherical particles, the dendritic structures are very kind of so is there some approximation to this?
Well, it's all an approximation actually, right?
Yeah.
I mean, because ultimately we're making one frequency dependent measurement that has a phase angle and a magnitude. And the rest is basically how you actually interpret that. And obviously there are a lot of approximations there and to see what works. But yeah, I mean, it's very hard to do the true size of it unless you start simulating it from small scale up.
And the structure is not creating a localized electrical field?
It does actually to a degree, but it spreads out, and we
Okay.
try to actually understand because we were thinking that there will be a big change with double layer overlap or not, and especially when we have nanostructures. But at one point, actually, we did cyclic voltammetry experiments and so on, and then we concluded that none of them were as relevant to our measurements. Yeah.
Very smart idea. Any other
But it's
questions?
not a uniform coating, so you
Yeah.
cannot control it very well.
Yeah.
Sometimes you overdo. Yeah.
Yeah, Carol. Yeah, sure.
But the dielectrical concept, the permittivity measurements for your new device is really cool. I just recently purchased the dielectrical property measurement probe. Have you confirmed confirmed your measurements for the different use a different system for the measurement of the
That's a good question, Carol. I agree, and I mean, we don't have a probe like that, right? So I mean, we measure the conductivity of the fluid. We can do that, and then we assume permittivity remains the same. Because it's an aqueous buffer. So no, we haven't directly measured, especially in the frequency domain, right?
Yeah, we try to switch but actually the problem is very has limitations, but how small the volume we can measure. Already bought large volume is actually pretty reasonable price. Now the smaller volume, the price jacked high. But at first level, but still has limitations. I don't think we can measure the volume you can measure. I just think, if we can confirm that in a certain range, then we can still learn from your system to measure small volume. So you can measure very small volume.
Yeah.
No probe actually, to my knowledge, no probe in the world can measure that.
I mean,
small
we're measuring in an indirect sense, right? We're actually measuring the variation of the impedance, and then we use an electric, modeling, circuit model. So the more richer your circuit model, the outcome may change quite a bit.
Yeah.
But then we also, of course, tune it with what theoretical value should be and so on. So those papers show like systematic way of handling this.
Yeah,
Yeah.
we need to follow you for that. Yeah, okay, collaborated with that. That's really cool. Thank you.
Thank you very much.
Well, if there are no other questions, let's thank Ali again. We have interesting gift as well for you. And
Oh.
with the duck, the goose,
the
so
goose.
hopefully it's not bothering you as you walk
No,
on
I
the
mean, it's a
campus.
rainy day, so I'm outside. Thank you very much, everyone.